So good morning, everyone.
Good morning.
I hope you can see. Okay, fine. I hope you can see the display of the document.
Yes, we can.
So today will be, last time we were talking about wave polarization. And there's something that I always talk about and I find students always forget. There's wave polarization and material polarization, and it's very important to know the difference, because many times you'll be asked to explain what wave polarization is and you get someone talking about, the displacement or distortion of charge distribution and so forth. This is not the case in this particular case. Now, today we are going to start on looking at how a wave behaves at material boundaries, because we know that at the end of it all, materials cannot be of infinite extent, as we have been talking about. Many times we'll find ourselves being near places where the material changes its properties. So what we want to look at are two important things, or three important phenomena that appear at that appear at the at the boundaries themselves, and this reflection, that is, the wave will change its direction and of propagation and go towards a different one in the same material, and then there will be refraction where the wave is transmitted into the second medium, but it will also have a change of direction. So we'll start straight away by looking at the wave reflection, and we'll look at two things. That is the plane of incidence and wave polarization. What do we mean by this? The plane of incidence is the plane that contains the direction vector and the normal to the interface or to the boundary of the two materials. So the plane of incidence is defined as a plane containing both the direction unit vector and the outward normal on the interface. Wave polarization can then be described as being, one, parallel polarization, in which case the electric field intensity or the incident electric field intensity is in the plane of incidence. That is, it is in the same plane as both the unit vector showing the direction of propagation and the outward unit normal on the interface. Or we could have what we call normal polarization, in which now the electric field, the incident electric field intensity is normal to that plane that is coming out. And any type of polarization can always be resolved into either a parallel polarized wave component and a normally polarized component as well, when we study wave behavior at interfaces. Now we consider a case where we have a wave with EI. We can see that EI is pointing out in the first, that is at the first wave here. We are just representing the direction of propagation given by Ni. The H field is parallel to the plane of incidence, and E is shown normal coming out of the plane of incidence. So the plane of incidence is the one which is carrying Ni and N. And therefore we see that it's the page that we are looking at. Now, parallel polarization therefore is shown by this this particular wave here, where the E field can be seen to be in the plane of incidence, and the magnetic field is normal to it. So this is material 1, and that would be material 2, and they would be differentiated by their constitutive parameters, that is mu, epsilon, and sigma. So in normal or perpendicular polarization, the electric field can be seen to be normal to the plane of incidence, and the magnetic field will have a component, therefore, in the direction of wave propagation in a similar way to what we would call a transverse electric or an H-wave case that we have already looked at when we were looking at the TE or the classification of waves. And therefore, the normal polarization may be termed also TE polarization in this particular case. The electric field itself is parallel to the horizontal YZ direction plane, and hence the normal polarization may also be referred to as a horizontal polarization. Now, in parallel polarization, the electric field is parallel to the plane of incidence, and therefore we expect that it will have a wave component in the direction of propagation, and this we call TM or E wave case. The parallel polarization may also be termed as TM polarization, and we can say that the electric field has a component in the vertical XZ plane, and this would be called, can also be used to define that polarization as a vertical polarization. Now, let's consider a case where we have normal incidence on a perfectly conducting plane surface. We assume that the wave is propagating from in the positive Z direction in a material that has constitutive parameters mu, epsilon, and sigma equal to 0. That is, the material is lossless, but it has scalar mu and epsilon. The other material that it's going to is a perfect conductor, and we call this a PEC, or a perfect electrical conductor. So the wave, we have a wave component which we'll call the incident wave, with EI and HI being the incident electric and magnetic field intensities. Once we get there, we assume, or we suppose that there will be a wave component that will be generated, and it will be propagating in the backward direction indicated by NR, and ER and HR indicating the field quantities. We shall see what these values are going to be. Again, we shall see that it may continue, the incident wave may continue propagating inside the other conductor. And we shall see that when we apply the boundary conditions and what we are talking about, the properties of the material, we shall see that this ET, or transmitted electric field intensity, and magnetic field intensity is going to be 0 in a perfectly conducting material. So let's assume material 1 or medium 1 is lossless, and the fields in medium 1 can therefore be indicated as follows. That is, we are assuming that our E field has an X polarization, okay, such that we have EI equal to X cap EIO exponent of minus j k1 and z. K1 is the propagation or the wave vector or the wave number in material 1, and it's propagating in the positive Z direction. And therefore the incident magnetic field intensity will be given by the direction vector, unit vector, cross the incident electric field intensity and divided by the intrinsic wave impedance of the material. And this we see that the HI will be propagating in the Y direction and given by EI 0 over eta 1 and the exponent of that. EIO or 0 is the magnitude of EI at Z equal to 0. So we also have that ER is going to be given by X cap. If you look at the definition that we have here, you can see that they are all pointing in the X direction. So the ER will be given by X cap. The exponent, that is ER naught, which is the amplitude exponent of J, K1, and Z. And therefore the HR is going to be given by eta R or NR, showing the unit vector in the backward direction cross the value of ER. And we see that that is in the minus Z Y cap direction. That is the HR, or the magnetic field intensity, changes direction at the interface. So the total field in medium 1 can therefore be given as E1 equal to the incident wave component plus the by the reflected wave components. The ER just means that we are reflecting it at the interface. And when we add them up, we just see that they are all pointing in the X direction. And H1 is going to be given by the addition, and we see that this value is going to be given by EI 0 over eta 1 exponent of that minus ER 0 over eta 1 exponent of that. So this minus sign, of course, is coming from the value that we have in here. You can see it here from the cross product of the unit vector, direction unit vector, and the particular wave value itself. And we shall see that the electric field and the magnetic field intensities will always have this relationship. That is addition, and that will be subtraction. So both the magnetic field, the magnetic and electric fields are going to be 0 inside the perfect conductor, because in a perfect conductor, if we were to have some kind of electric field, the free carriers will be accelerated away, and we'll have currents flowing in there, and most of the time they'll end up at the surface of the material itself, okay, where they cannot flow anymore, and therefore we'll have a surface charge on the surface of the perfectly conducting wave. And since the electric field is time dependent, we expect from Faraday's law of induction that the magnetic field should also go to 0, because the E field is equal to 0. Okay? So the continuity of the tangential components of the total fields at the interface will require that the EI, okay, the incident field plus the reflected field must be equal to the transmitted field, which we said was going to be equal to 0. And we can make the conclusion that the reflected amplitude of the wave is going to be the minus of the reflected of the incident magnitude, okay, electric field magnitude in there. And therefore, we can add our values in there, and we see that this is just going to be the minus of X cap J 2 and the exponent of I0 and the sine K1 of Z. And what we can see is that now the wave will be stationary in space and will be varying or oscillating as a sine wave as we measure distance from the interface into the medium, that is the lossless medium. And the H1, or the total field in medium 1, is going to be given by twice EI 0 over eta 1 and the cosine of K1 Z. What we can see is that the E field and the H field are in time quadrature phase, because this is multiplied by J and this one does not have a J. Okay? And we can see that they are also in spatially orthogonal to each other. And therefore, we can say that E1 and H1 in terms of Z is in quadrature time phase, and the resultant magnetic wave transports no average power. The wave is called a stationary wave because when we take the instantaneous expression for E1, which is the real part of E1 multiplied by the exponent of j omega t, we just see that it's just going to be given by twice E1, EI0, the sine K1 of Z, and the sine omega t. If the wave was propagating or was changing with time, we should be getting a minus K1Z somewhere, but we don't have minus KZ in this particular case. And therefore, the wave can be seen to be localized in space. And so we can see that also the magnetic field intensity has a similar kind of equation, only that it's varying as a cosine. And therefore, we can say that it is spatially fixed and is oscillating as time evolves. So amplitudes of both the total electric and magnetic field intensities will show zero values and maximum values at fixed distances from the interface, which we have put at Z equal to 0 for all time. Specifically, what we can say is that the zeros of the magnitude of E1 and the maxima of the magnitude of H1 will occur at positions K1 multiplied by Zm equal to minus n pi, okay? And we are using the minus because the Zm is measured in the negative Z direction from the interface. And therefore, we can conclude that those positions Zm are going to be given by the minus of n gamma lambda over 2, where lambda is the frequency, okay, or is the wavelength of the wave in space. And for n equal to 0, 1, 2, and so forth. Therefore, it means at the interface, the electric field has a 0 or it vanishes as the boundary condition requires. The maxima of E1 and the zeros of H1 will occur at the same plane and given by K1, and I'm giving it as Z big M equal to minus 2n plus 1. There's a bracket missing there, pi by 2. Or in other words, Zm is going to be given by the minus of 2n plus 1 eta over 2, where n is equal to 0, 1, 2, and so forth. So here we have half wavelengths, and here we have quarter wavelengths for the maximum. And this can be seen in the case that we have seen that E1 of Zt is varying as sine K1Z, okay? And therefore, it will be maximum where the K1Z, where K1 is equal to twice pi by lambda. We shall see that this will be given by pi by 2, so to speak. So one example we have here is that a Y-polarized uniform plane wave, E1I and HI, of frequency 100 megahertz is propagating in air in the positive Z direction and impinges normally on a perfectly conducting plane at Z equal to 0. Now, assuming that the amplitude of EI, or the incident electric field intensity, is 6 millivolts per meter, write the phasor and instantaneous expressions for A, the incident electric and magnetic field intensities, the reflected and electric and magnetic field intensities, and the total electric and magnetic field intensities in air, because that is where the material or the wave is propagating from. And D, we determine the location of the nearest conductive plane, okay, the nearest location where plane where E1 is equal to 0, apart from the position of the interface itself. Okay, we have said that at the interface, E1 is of course going to go to 0, but we are looking for another one where it will be equal to 0 but closer to the interface. As a solution, what we do is that first of all, we look at the information given. We have been given the frequency as 100 megahertz, and therefore we can get the radiant frequency as twice pi multiplied by 10 to the 8 radians per second. And therefore we can obtain the value of K1. We know that the medium is air, and therefore the omega by C is just twice pi by R. I would suggest that we don't express this, use our calculators to get the actual decimal values of that, and we leave it as it is. The eta 1 will be given by mu naught by epsilon naught, and this is approximately 120 pi ohms. And therefore, E1Z is going to be given by Y 6 millivolts per meter exponent of minus J 2 K pi by 3 Z. So that's how it would be behaving in that particular case as a phasor. And the magnetic field intensity is going to be given by the direction vector, because the unit vector is in the, we are propagating in the positive Z direction, therefore we use the Z cap and cross EI and divide that one by eta 1. And what we get is a minus of 0.1 by twice pi, the exponent of minus J twice pi. I think this says it should be a Z direction here, not X, and milliamps per meter. So this is an error that I have there. So, and therefore, when we take the instantaneous values, we just use the phasor representation multiplied by the exponent of j omega t and take the real part. And once we do that, we'll just get the omega t minus the K1 multiplied by Z in millivolts per meter, and the H1 is going to be given by that equation as well. And we see that they are all cosinusoidal. Now, for the reflected wave, we saw that at a boundary, at a perfectly conducting boundary, the magnitude of the reflected wave is the negative of the amplitude of the incident wave. And all we have to do is just multiply that one by minus sign, and we get the similar value like for the EI. And then for the other one, we have that. But notice, now we are moving in the backward direction, and therefore we don't have a minus here. And therefore the instantaneous values are just like before, and you see that we have that as a wave propagating in the negative Z direction because of that positive sign there. And so the magnetic field as well. And part C, the total fields, we just add the incident wave plus the the reflected electric field, and what we get is just that value, okay? And H1 will be given by the minus of X, and that over pi, the cosine of twice pi by 3Z, so that the instantaneous values are just multiplying those through, okay? And we see that because of this J, okay, we'll get a sine wave instead. And while the magnetic field intensity is propagating with a cosinusoidal kind of propagation here. So the electric field vanishes at the surface of the conducting medium at Z equal to 0, and in medium 1, the first null will be at Zm equal to the minus of lambda 1 by 2, and this is going to be given by the minus of pi by K1, and it's equal to the minus of 3 by 2, or 1.5 meters from the interface. So you see the beauty of leaving the pi's without evaluating them, because we know that somewhere, everything, if we leave the pi's there, the pi's will cancel somehow, and you'll get very nice values, instead of just first sitting down and computing that, writing it down, then later all your work will be negated as you cancel things. Now, we look at an interface, a similar interface, but we assume that although the conductivity is large, it's not infinite. And therefore, we expect there will be, the wave will not completely vanish at the interface, but there will be some penetration of the wave into the good conductor. The situation otherwise is similar to what we had before. So in this case, we can write that the similar equations like before, and we see that we have not changed much, and we have the same value, so to speak. So, because the conductor has a large but finite conductivity, then the field in the conductor must satisfy the diffusion equation, where and it will decay with distance from the interface as the exponent of minus z divided by the skin depth into that material. So we can therefore write that the ET, or the transmitted electric field intensity, will satisfy the diffusion equation, where we have this gamma squared given by the j omega mu sigma. Okay, where we are saying that the displacement current is very small, and therefore the omega squared mu epsilon can be neglected in this particular case, and we are just left with this value here, the damping value. And we saw that the propagation constant in that case is going to be given by that value there, and we see that it has now becomes a complex number rather than a real number or a purely imaginary number of quantity. And therefore, E of t is going to be given by exponent of ET0 at this interface times the exponent of minus gamma z. It's flowing or it's moving in the z direction as well. The H field will be given as the curl of ET from the Faraday's law of induction and divided by 1 by j omega mu, and we see that that is just going to be given by gamma by j omega mu, and we can see that this gamma by j omega mu can be defined as an impedance for the good conductor, and we give it an eta m there. And eta m is therefore going to be given by that equation there, and you see that it's just going to be given by 1 plus j over sigma multiplied by delta s, which we can write in real and imaginary parts as Rm plus Jxm. And we see that Rm and Xm are equal because Nm has a phase of 45 degrees. So Rm is usually called the resistance in ohms per square, and it's the resistance, the surface resistance of the good conductor. So once we look at the continuity of the tangential components, and look here, the tangential components we are talking about are of the total fields, not the individual fields, but the total fields. Okay, so the tangential components at the z equal to 0 must go to 0, but must be equal. That is because we say that the tangential electric field intensity is continuous across a material boundary. Okay, or an interface. And therefore, we can see that EI0 plus ER0 is now going to be given by ET0, which is the amplitude of the transmitted wave at the interface. And the magnetic field intensity, okay, the tangential component of the magnetic field intensity must be equal to the magnetic field intensity of the inside the good conductor. Okay, so ET0 and EI0 can therefore be expressed in terms of EI0 as follows. We define a transmission coefficient into the conductor and give it the symbol tau, and define tau as the amplitude of the transmitted wave into the material at the interface divided by the amplitude of the incident wave. And this we can see is just going to be given by twice eta m over eta m plus eta 1. And this, if you remember your reflection or your transmission lines treatment in third year, you can see that this is the same as having a transmission line, okay, terminated in a load eta m, and the transmission line characteristic impedance is eta 1. And you would get the same value of transmission coefficient. Okay? Now, if you look at the reflection coefficient from the interface and give it gamma, we can define it as the reflected wave amplitude at the interface divided by the incident wave amplitude at the interface as well. And we see that once we do that, we just get 1 minus eta 1 by eta m multiplied by the transmission coefficient and divided by 2. And once we replace the value of the transmission coefficient, we just get eta m minus eta 1 over eta m plus eta 1. Again, this is a very important relation, because you can see in terms of transmission line, this would be the terminating load, and that would be the characteristic impedance of the line. And therefore, we shall see that later, wave propagation in unbounded media can be modeled as a propagation in a transmission line. And therefore, we can write that ET of 0 is just a tau by EI 0, and ER of 0 is just gamma EI 0. That is the reflection coefficient multiplied by that value of the incident wave amplitude. And we note the following, that if we were to add unity to gamma, we'll get exactly tau. Okay? And this relation is important to always keep in mind. Note that eta can be negative, or that gamma can be negative or positive, okay, because of the way it's defined here. But since these are real values, tau can never be less than 0. It can never be negative, but gamma can be negative. Okay? So, in many practical dielectric good conductor interfaces, at the usual frequency range of interest, that is below optical frequencies, the magnitude of eta m is usually much smaller than the magnitude of the dielectric intrinsic impedance. And therefore, in such cases, you have that gamma is just going to be approximately minus 1, and tau is approximately 0. What we are saying that the penetration of the fields into the good conductor can be neglected, and there will be total reflection of the incident wave at the interface. Now, if the conductor thickness in the direction of wave propagation is at least several skin depths, the current density that is induced in the metal will decay exponentially with distance from the interface. And therefore, we can write that J, the total J, is going to be given by the conductivity of the material multiplied by the electric field, and we see that that is just going to be given by sigma tau EI0 and the exponent, the minus gamma and Z. That's how the J will be attenuated in the direction of Z. The total current per unit width of the conductor in the Y direction will therefore be given by the integral from 0 to infinity. By putting infinity here, we are just saying that since the conductor is so thick, is thicker than several skin depths, by the time we get to the back face of that conductor, the field will have decayed to 0 and the current will be 0. And therefore, if we extended the limit of the upper limit of integration to infinity, we'll just be essentially adding zeros into that sum. Okay, and therefore, once we do that, we see that the Js, or the surface current density, is just going to be given by sigma tau over gamma multiplied by the amplitude of the incident electric field intensity. In the limit, as we make the sigma to go to infinity, that is, as we get better and better conductor to get a perfect conductor, then we can see that J of S is just approaching EI by 0 divided by eta. This will be called a surface current density. And therefore, for a perfect electric conductor interface, which we call the electric wall, and described by the tangential field intensity or magnetic field intensity vanishing, and the tangential magnetic field intensity must be equal to, is discontinuous at the interface, with the discontinuity equal to the value of the current at the surface. N, in this case, is defined outward, okay, outward on the conductor interface. That is pointing into the air or the dielectric at the interface. So the magnetic field will be tangential to the conductor surface, and we only need to evaluate it at the surface of the conductor from the continuity equation. And since the tangential field intensity is continuous at z equal to 0, then the result will be the same as h is determined just outside, whether we determine h outside the conductor or just inside the conductor itself, we should get the same. So the expression for the electric or for the reflection coefficient is similar to one that is obtained in the case of a voltage wave traveling in a transmission line of characteristic impedance eta onto another one of characteristic impedance z or eta m. And therefore, we can always model our wave propagation in a bounded medium as a transmission line in the following form, where we have one transmission line with a characteristic impedance eta 1 and another the transmission line with a characteristic impedance eta m. And I'm showing that this one is the separation of the transmission line, whatever conductors is larger, because eta m, of course, we have seen is smaller than eta 1 there. So how does what happens, how does the power get transmitted into a good conductor? So what we do is that we define a Gaussian surface around the interface and pointing into the good conductor. And we want to see our wave is moving in that direction. We have the perfect conductor on this side and the good conductor on the other side. We define our normal vector, okay, the normal unit vector as pointing into the volume, the shaded volume that we have dealt with, okay? And this volume is defined by the surface S0 and the total surface, which will be covering, a tube, S. This S also contains the end cap for that volume as well. So the time average power that is entering the volume is of course obtained from the Poynting's theorem, and we saw that the Poynting's theorem was that the Poynting's vector, the average Poynting's vector, was given by a half the real part of E cross H conjugate and multiplied by the ds. Now, to get the average value, it's over the surface, and therefore we are integrating over the closed surface S0, defined by S0 plus S, and we do the P average, the Poynting vector average, and multiply by that, and what we get is just the P average multiplied by that. So eta is the n cap is of course the unit normal pointing into the volume on the bounding surface S0 plus S, and E and H are fields that we can define at the inside surfaces of that volume. Now the contribution to the P average through the surface S, we can always make it to be arbitrarily small by choosing S appropriately. Now, if the wave that we are dealing with is a uniform plane wave and it's incident normally on S0, then the Poynting's vector will be in the direction of propagation, which is in this case the Z direction. And therefore, if we were to do E cross H dot the surface, we can expect that since eta, or the n cap, and the vector that define this are parallel, then we can are normal to each other, then the dot product is going to be equal to 0 on the parts of S that will be parallel to the Z direction, the Z axis. Now, for a good conductor, the transmitted fields will decay rapidly from the interface at Z equal to 0. And what we can do is to make the end cap, okay? We make this end cap here. Now, these ones are parallel. We make them parallel. And then we pull this very far deep into the conductor, such that by the time the wave reaches that point, the fields have decayed to 0, like we have seen already. Okay? And therefore, we expect that the end cap of S will be sufficiently far from Z such that its contribution will be negligible. And therefore, if we were to say that the radius of curvature of the conductor, if the conductor is cylindrical, is at least a few skin depths, okay? If its radius is at least a few skin depths in magnitude, the power absorbed in the volume will be given by the P average equal to that value there. And we can see that we can reduce this into its value, that is Z cross E. All it's missing here is we multiply it by the intrinsic impedance of the medium, and we'll get H. We divide it by the intrinsic impedance of the medium, and we'll get H, so to speak. Okay? And therefore, this is what we have here as eta M cross multiplied by H and multiplied by that, and we see that it's just going to be given by eta M and the magnitude of the surface current density, okay, the real part thereof. In other words, the P average is just going to be given by Rm, that is the real part of eta M, divided by 2 and the integral over the S naught, and multiplied by the magnitude of H. And we know that the magnitude of H is equal to the surface current density at the interface, and we can really raise this like that. So Rm is of course given by the real part of eta M, which is equal to the real part of 1 plus J and that. And this is the value that we have that places. This is an important result to keep in mind. So we call it a surface resistance, and it's always measured in units of ohm per square. The best thing you can recall is, of course, your PCBs that you use to make your, what are they called? The ones you use to do circuits, to create circuits on it. It will be having copper clad with a thickness of about 18 ounces or 18 microns, and the rest, if you are to look for its resistance, then you'll have to look at its resistance, whatever definition in ohms the specification in ohms per square. And this means that a kilometer by kilometer square of that conductor and a nanometer by 1 nanometer square of that conductor will have the same value of Rm. If the shape of the piece that you are dealing with, the layer you are dealing with is different from a square, then you can't use this value, okay? You'll have to get its actual resistance, okay? So it's specified in ohms per square, and therefore you can look how many squares can fit in that particular component you have, or that geometry you have of conductor, and then you can get its total resistance, okay, so to speak, multiplied by its thickness, and you're okay. Now, we want to look at how it will behave when we are looking at oblique incidence. And before I go to oblique incidence, I'll give you a few minutes to try and reflect, and then we can discuss if there are any issues. So do you have any issues, or I can just continue? Hey, are we in class, people?
No issues.
No issues. So then I can look at the oblique incidence. What we were looking at is where the wave was attacking the interface with normal incidence, that the angle of incidence is 0. Now we want to see, suppose that the angle of incidence was different from 0. That is, the interface is at a different angle to the direction of propagation of the wave. This always happens, especially when you are looking at, at a television screen from the side. Many times you'll see a reflection of the furniture rather than the picture that you are meant to see because of the reflection at the glass interface. So what we need to understand is that for this particular case, the polarization of the wave is important. For normal incidence, whether the wave is parallel polarized or normally polarized, okay, with the polarization defined in terms of the plane of incidence, it doesn't matter. It will just give you the same results. But when we have oblique incidence, we shall see that the reflection and transmission coefficients of the interface will depend on the polarization of the incident wave. So we recall that the plane wave may be either normal or perpendicularly polarized, or what we call a TE or horizontal polarization, or it may be of a parallel or TM vertical polarization. Now let's look at a normally polarized incident wave, or EI, that is normal. That with EI, of course, is normal to the plane of incidence as shown below. So here we have EI, it's pointing out of the page, okay, or the screen, and the wave propagation direction with respect to the Z direction is at an angle theta I. So we expect that the reflected wave will be refracted with an angle of reflection theta I, and therefore it will be pointing backwards into the original material, but at a different direction or angle of reflection, which we are calling theta I. For the transmitted wave, it will be transmitted into the conductor with an angle, and it will change its direction with theta t. This is expected because the speed of propagation in the two media will change. So from the geometry of consideration of those equations of the structure, we can see that Ni can be expressed in terms of x and z, and we see that this angle here will be the same as theta I. Okay, and therefore x will be the unit vector in the x direction will be, that is, the unit vector Ni will be given by x cap multiplied by the sine of theta I, and then it will be moving in the z direction as z cap, the cosine of theta I. The same thing can be said about Nr, okay, but we'll see that it's moving backwards, okay, but it's going upward, okay, in the x direction. So we have x cap, the sine of theta r, minus z cap, the cosine of theta r, okay. The H field as well can be done the same way. We know that the H field is perpendicular to the direction of propagation. Therefore, the angle, this angle here must be what? This angle must be 90 degrees, and therefore this must be this one is theta I, that will be theta I, 90 minus theta I, and therefore this must be theta I itself. And therefore this can also be resolved into a Z component, okay, and an X component, so to speak, for HI. So we see that the direction unit vectors eta I will be given by those expressions, and it's important that you know how to resolve that. And two, the position vector of the field point, that is where we are observing the waves, will be given by r cap x plus y cap y plus z cap z. This is the position where we are measuring or observing the wave itself. Okay, that's the observation point. So in medium one, therefore, the incident field intensities will therefore be given by y cap, because of the way we have defined EI on the diagram. It's polarized in the y direction, normal to the plane of incidence, and therefore it's going to be given by I naught minus j k1 and NI cap, that is the unit vector in the direction of propagation, and dot that value, that is the projection in the direction of the observation point. And once we do that, what we get is just that value there, and we see that inside we have x sine theta I plus z cos theta I. The magnetic field intensity will be given the same way as n cap, the direction unit vector, cross the incident electric field intensity and divided by the intrinsic impedance of the medium. And once we do this, we'll see that this value is going to be given by the minus of x cap cosine theta I plus z cap sine theta I, just like we saw before, but just by looking at the diagram. And this is mathematically, we now confirm that our suggestion is correct, and therefore we multiply that by the initial case. For the reflected intensities, we'll use the same value, but because we are using NR cap, the direction vector here, we should show that it's going in the positive NR cap. That is in the R direction, in the NR direction, or the direction indicated by NR. Okay? And therefore we'll use the minus j k1, whatever, multiplied by that, rather than using a positive value here like we were saying when we are going in the positive z direction or negative z direction, we just multiply by the z. So we are using the direction vector as defined, and therefore we have those kind of equations. And once we spread them out, we see that that is going to be given by that value there. And H, or the magnetic field intensity that is reflected, is again the direction unit vector cross the reflected electric field intensity and divided by the intrinsic impedance of the medium in which the wave is propagating. And since we are still in the same medium one, then that value is eta 1. And that gives us this following value here. So in medium 2, the field intensities are of course given by ET equal to y cap and multiply by that. And we can see that that is just going to be given by the minus gamma and multiply by those values there. And H is the same as, is similarly given by those values, where we are using the intrinsic impedance of the second medium, which was said to be a good conductor. And therefore, as before, this field will be vanishingly small for good conductors at the usual frequency of interest, because eta m will be very, very small, and the field will just be at the interface, that is at the boundary, the surface of the good conductor. And we can always ignore this field when we deal with it, and that's what we are going to do now. And therefore, if we use the continuity of the tangential components of the total fields at the interface, then we must require that EI at x of x in the x direction at 0, at z equal to 0, plus the reflected electric field intensity as a function of x at z equal to 0 must vanish, because we have said that ET is very, very small. It's a good conductor, but at the frequency of interest, it can be taken as a perfect conductor. And therefore, we can see that this equation, okay, that is EI0 exponent of minus JKX sine theta I plus ER0 exponent of minus JK1X sine theta R must be equal to 0. For this to hold for all values, okay, for all values of X along the interface, then several things must be said about this equation. Then the exponent of K1X sine theta I and the exponent of minus JK1X sine theta R, they must be the same. If they are different, then this addition will never go to 0. Okay? So, we can say that for it to hold for all X, then the phase propagation factors given by exponent of minus JK1X sine theta I and exponent of minus JK1X sine theta R must be the same. They must change with in space as X varies in the same way. And therefore, this can only happen if theta R is equal to theta I. Okay? So this is what you call the Snell's law of reflection at an interface, that the angle of reflection is equal to the angle of incidence that you already covered in physics. The next thing, if that is the case, if those and that are equal, then EI0 plus ER0 must be equal to 0, and therefore it means that the ER0 must be the negative of EI0. And once we have that, this is just the statement that I've just made a few minutes ago, that the Snell's law of reflection is that the angle of reflection is equal to the angle of incidence. And therefore, we can see that the reflected electric field intensity is going to be given by just the minus of y cap EI0 and the exponent of that value, and the magnetic field will, of course, the direction of a unit vector cross that value and divided by eta 1, and we see that it's just going to be given by the minus of EI0 eta 1 and multiplied by that. And the total field intensities are therefore going to be given by E1x of z is going to be given by that equation as a phasor, and magnetic field intensity as well as a phasor. And we see that we can have an amplitude that depends on the position of the plane from the interface as given by K1, okay, cos theta I multiplied by z. But then there's also another value of minus JK1x sine theta I. We shall see that this will represent a propagating wave in the x direction, that is along the interface. Okay, and the magnetic field intensity as well, we have a similar kind of value happening in that case. Okay, so we note the following way. In the z direction, that is normal to the interface, the E1y and E1x, that is the y component of E1 and the x component of H1, are standing waves with amplitudes that vary with distance from the interface according to the sine of K1z cos theta I and cosine of K1z cos theta I respectively. The E1y, okay, the y component of E1 and the x component of E1 of H1 are in quadrature time phase. This can be seen from this case. We have a j for E1y, okay, and this j causes is a time phase of 90 degrees. Look, the z component of H1 also has a time quadrature phase here. So therefore, we shall see that E1y and H1z are in phase. So in the x direction, that is parallel to the interface, E1y and E1H1z are in time phase because they both have a multiplication by j, and they have spatial quadrature phase because H1 is pointing in the z direction and E1 is pointing in the y direction. So they are orthogonal to each other, and therefore they are transverse electromagnetic waves. Okay? And they propagate, okay? The wave propagates in the positive zx direction with a phase velocity given by v1 of x, given by omega over k1 sine theta I, equal to v1 over sine theta I, okay? And we see that this velocity will be larger, okay, where v1 is just omega by k1, which is in the unbounded medium, okay? And therefore we can see that this will be larger than the velocity of light in that particular medium, okay? And the wavelength will be given by that value. So the wave will be described as TE, okay? Okay, because it has a wave component, okay, a component of the magnetic field in the z direction or in the direction of propagation, so to speak, okay? And therefore we can call this perpendicular polarization, as we describe it as TE polarization. The wave propagating in the x direction can be seen to be a non-uniform wave because its amplitude varies with position from the interface, that is, varies with z. So since E1 is equal to 0 for all x, when sine k1z cos theta I is equal to 0, that is, for k1 zm cos theta I equal to a value minus m pi, where m is equal to 1, 2, and so forth, a conducting plate can be inserted at any of these planes described by the m1, 2, and so forth without changing the field distribution within between the interface at z equal to 0 and this conducting plate that we have introduced. Okay, and the TE wave will therefore bounce back and forth between the plates and propagate in the x direction. This is, we shall see in the second semester, that it describes what we call a parallel plate waveguide. So example 2. So a uniform plane wave with electric field intensity and magnetic field intensity E1I and HI with an angular frequency omega is incident from air on a very large perfectly conducting wall at an angle of incidence theta I, and it has perpendicular polarization. Find the current that would be induced on the wall, okay, on the wall surface, and B, the time average Poynting vector in medium 1. So that's what we want to find out. Remember, once you see current induced, all we are asking you to remember is to use the continuity or the boundary condition for the tangential and normal fields at the interface. That's all we are trying to test when we ask for the current. So the solution process goes as follows. We assume that EI has a polarization in the y direction because it's normal polarized, and we are just using our structure so that the normal polarization is in the y direction, so to speak. And therefore E1 at x at 0 is equal to 0, and H1 x at 0 is just going to be given by minus EI 0 by eta 1 multiplied by that value and multiplied by that. So since inside the conductor both E2 and H2 will vanish, the magnetic field is discontinuous across the boundary with the magnitude of discontinuity equal to the step in the surface current. That is, if we were to define the unit normal on the conductor to be N2, we can see that N2 is going to be the same as the minus of the z of the unit z, the unit vector in the z direction. So that is the outward normal on the surface from region 2. And therefore, the surface current density will be given by N2 cross H1, and we see that is the minus of Z cap cross minus X cap, and multiply by that, and we get that value there. So the field is that the current density is therefore going to be given by EI over 60 pi. We are using the intrinsic impedance of the medium, okay, of the lossless medium, eta 1, and we used twice, what we call it, with 120 pi ohms. And since we have twice value here, cos theta I, we are just going to get 60 pi down there, okay? And in the end, you can see that the instantaneous current induced in the surface is just going to be given by the usual thing we always say: take the phasor expression, multiply it by exponent of j omega t, and take the real part, and this is the expression that you are looking for. So this current will be induced on the wall surface that establishes a reflected wave. Okay, this will be a source of the reflected wave that will propagate into medium 1 and will cancel the incident wave at the conducting wall. Okay, so we shall see that when we talk about scattering or reflection, we can also say that we can use the currents as the sources that are, it's like a radiation of a field. So in part B, we are saying that E1y and H1x are in time quadrature phase, and therefore the average value is going to be equal to 0 only for the case where E1y and E just arising from E1y and the Z component of the magnetic field. That's what will give us an average value for the Poynting vector there. And this will be given by that value there, and we see that it's just going to be given by EI0 squared by eta 1 sine theta I and sine squared K1 and multiply by cos theta I. But suppose we have parallel polarization, and I think you are not alerting me, but I think my time is now up, if I'm not wrong. So I think I'll stop there and look at the parallel polarization tomorrow. So do we have any issues?
No.
So I'll request that you go through the material, because I already uploaded this. I already shared in the drive, so you can always try to follow it. Then we can look at the oblique the parallel polarization case with oblique incidence. Now I need to go to the lab. So I'll wish you a nice day. So we meet tomorrow.
Thank you.
Okay, bye.